telespectrum. So that's what. Yeah. So that goes to
Okay. Now you share the screen.
Okay, while she's setting up the things, uh, good morning, everyone. Um, so yesterday you had two talks on the artificial neural network. First one was more of introduction, and second one, Professor Kamari went slightly deeper. What I am going to talk today, actually, the topic sounds little then and now, and then and now has important reason here. See, as we will go along in the talk, um, artificial neural networks actually started even 50s and 60s earlier. The problem with that time was the computers were too slow. So it was not a new thing when we started doing this in the early 90s. I had just joined IUCA at the time, and we were essentially stars and spectrum. So we started doing something, we developed our own code written in pure Fortran process and even later plus. Later on, nowadays, as I'm showing the exercises here, Python. But actually, Python came much later. The codes written for neural networks are in MATLAB, but obviously MATLAB is a paid version, so you can have hacked version, but Python is easy and it sets up fine. Even I myself don't know Python much in the sense if some student has done something, I can wear a little bit. Earlier, I was using mostly for problem, but now, so that's where the whole point comes about machine learning and all that. And it's a general word. No, machine learning is a general word. Actually, there are a lot of things inside that. Some of it were mentioned by as yesterday. Even the things we are doing now, everybody is aware of ChatGPT, but there are these sites called Grok. I'm sure you're not aware of it. It's done by Elon Musk, and there is a competitive site, some Chinese site. I have not tried that. It's even better. So these are all versions of future. That's what feedback is. So you can
actually your column I should not go and her it is speakers. There's a feedback. So you can send yourself something.
Yeah.
See how this happens. You're close to any speaker.
Thank you. So, I'm going to talk then and now means when I said then it was in early 90s. And we were kind of pioneers in this in the sense that before us there was only one publication on artificial neural network, and that fellow, I met him later after many years. He is into stock market. See, these things are being applied in such wide variety, including biology, and I will use some examples of that. So they were pioneer in the sense they did what is called one-dimensional classification. So by the way, neural network is not used for classification, but many other things. So when we started, we did something called spectral type classification and also reverse. Where the identification, and later on over the years, was decade almost if 2010 or something. There were many new applications where we applied it. And I will show a whole lot of these new applications. And of course, the future of this is already seen. You are using this. For example, just to be on the reality side, when you are using these modern things like rock and all, you have to be very clear. See, it will do everything for you, but whether it is good for you, whether the results you show are correct. That is the most important point. And that's where we come in the picture. You can leave it to the machine to do it. But when you are writing some query, the machine will is answering, not a person. And there are some options where person will, of course, 24 hours all over the globe. It's a machine which is. So I use it as you will see, use it in the last 1 year I started using it. on a different kind of application. Okay, so slide.
This one, actually, because it's a PDF, na? Ah, okay, so.
Slowly.
Yeah.
Fine.
Then I need
Right.
to see.
Okay, so friends. So, I think this slide can be all.
Yeah.
It is contrast.
Yeah.
So, as I was already mentioning, there's been more than 4 decades or even more, and only the recent years has gained importance in their usage, like face recognition, which was introduced yesterday, stock markets, I already said, biological applications, and it's now probably known as AI and machine learning and all that. I mean, each one is not exactly the same, but they fall under the umbrella of neural networks where it started. So what I will describe is the basics of AI in astronomy, particularly classification of spectra, and deducing various parameters from that. And as I said, in the early 90s, we started this, and we have been doing very wide range of applications. And the new things which Ajit was mentioning is deep learning, convolution ANN, then quantum computing, basic classification, chat GPT, and Grok. So, at somewhere here, they are all using particular neural networks. So this is just a outline plan, introduction, some applications. The ANNs, why it was required first for classification, and then several applications and the future of. Okay, so this, I mean, now if you go to Google or you can open an ANN book, the basic things they will talk is it's actually a statistical mathematical tool. And the earlier part before ANN was nearest number, basically chi-square. So you reduce the, if there are two curves following each other, and one of the curves is a model, you keep varying, the nearest one should have the minimum chi-square, the minimum distance, will be the best suited. And this is also doing similar thing, but in a much more complicated way. And more importantly, it does it very fast. I'll come to that. So, and this was also described, I will also describe some interconnected processes and so on. Most importantly, the kind of thing I am talking today is the supervised learning, where you have set of data on which you train the network, and training takes a while. So each application training may be different. The kind of layers and things like sigmoid function is studied. So various things can be tried, but it turns out that sigmoid is the best option. And the name of neural network is actually inspired by the structure inside the brain. And they look very similar to the pattern solution. And it is always requiring some kind of a input from the expert. So suppose I am a user, I will tell the computer this is the correct classes, and when it goes through that, comes to the list. What is unsupervised, which I will not talk, but some of my students did it sometime back. It seems unsupervised is much more faster. Not only faster, it has better classification. And the basic thing about unsupervised is exactly like a child, uses a cube or a ball. So it starts learning shapes. So you can also say it's a pattern recognition tool. That's where the face recognition is actually a pattern. So again, in a biological system, there is a neuron cell body, and I'm not going into these biological names, but essentially the similar name. So this is the biological sketch of a neuron. But you will see so this is again that, but you will see this. So this is the mathematical version of the neural network. I have a better picture. I'll come later. So the idea is there is something called input layer where you put in all the training. So this is for the training session. So suppose you have ABCD sequence. Okay. So ABCD are the characters, and that's in the input layer. And there is something in the Indian layer which does all these interconnections. And output is again ABC, which means when B should not be classified as C, for example. So after doing this training, several thousands, the computer learns when an unknown pattern comes like Z, so it should go to Z, it should not go to A, for example. And they do have errors, and there are outliers, so we come to that. So not that everything is perfect, and even today, I think, I can check, it's not 100% good. And also, many people think, commerce, that it's a black box. But if you go a little deep into it, it's not really a black box. But at the same time, each application it will be different. So if I do stellar spectra, if I do the phase recognition, the exact number of layers are all can be different. And that's why the training and the initial things take time, sometimes several days. But once the training set is trained, I will tell you what it means by training set is trained. After that, if millions of people come, their faces will fall into the category. So all those things are later stages. So yeah, see, this picture looks very much like the neuron thing. So this is the input layer, this is the output, and there are interconnecting layers and there are weighted connections. And so essentially, you can think it like you are sitting in, let's say, in this one area, and you are coming from some other part of Hyderabad. So there are several routes, okay? The shortest one, let's take, like the Google says, shortest route, Google Map, maybe this one. But all others are also possible, except that their importance, which I call as a weight here, is less. So if you make an array of those lists, the only shortest one in my government right now is the shortest. We'll have the maximum weight, but all others are still there. They will much less. To do that, it takes training, right? Because you must attempt all of the rules, see the traffic, and so on. So that's basically what it is doing. And this was mentioned, the second one, sigmoid, is the mathematical expression of that. This turns out to be the best option because it smoothly connects one layer to the other. There are other options, but at least in my experience over 3 decades, the best one is still sigmoid. But maybe there is some application where other connections are made. So this is the function. And see so when again going back to simple ABCD example, when a B pattern comes, it goes to sigmoid, and then the output it has to be B. And if it is not B, then the difference, suppose it is C. So B minus C is the error function. What is the difference? The whole idea is if I keep on repeating this, the error function has to be used. And then you will think that the training is complete. So this is that error function. And this is the mathematics department. So I don't have to go deeper into this. So this was mentioned by Devavi also. So these are all the notations. So to be frank, in 90s when we did this, me and my colleague, we developed a simple program which you can see or Python. We actually went step by step and developed the code. The code is actually on my laptop. Even today it works. And these are all the details of that. And so we are talking about supervised learning. So they will take the training set, different sets are there. And I will not talk about unsupervised where it also does this weights and all, but it's the user or the person who is defining doesn't have control, which means the network itself will know this is a cube, this is a star or a sphere. So over time it recognizes just like a child learns things. So I will describe a bit about training and testing sessions. This requires the training data set as example inputs, and the output is the desired output. It consists of passing the data through these different layers, which I explained. And this was also mentioned. There is something called back conversion. So if the error is large, it again goes back to the and it keeps doing this. So that's why it's called multi-layer back conversion. There are other models which the exercise are related. In Python, you have those. So then, as the error is coming down, there is something called learning curve, maturity. And on the x-axis, you have number of iterations. So it depends, sometimes 1,000, sometimes 10,000 iterations are required for the RMS error. Okay. And that is important because then you know that the learning is over. How good the learning is, the only way to check is to use the training data on the x-axis and the y-axis. The output should be perfect. Diagram. Okay, all the points on that. Some of these words will become clear when we see that. And once the training is done, the weights are in this language called weights are frozen. So the computer knows which path is more important. Then if you have an unknown spectra, millions of spectra, like yesterday was taking, when we were doing these things, the telescope data were limited, but now you have huge amount of data, in a single night, in a single hour, many parts of the sky, the spectra are taken, and after analyzing it. So human person cannot do this kind of classification. In fact, when the whole classification thing happened in about various back, in fact, interestingly, for the girls here, there were two lady astronomers who were painstakingly checking the things, matching. So literally, humans were involved in classification. The only difficulty there was those two ladies are now, of course, but even during that kind of, for some reason, I think both of them are sick. Somebody else does that. You will have a different bias because it's a human-centered thing. Here, there is no human component; it's the computer. So, in that sense, it's much more reliable, much more robust. Okay. So, this is actually a curve of a learning curve. The data is something smaller, but I will explain. Here, the x-axis there are numbers, and why the numbers are there, I will tell you because some of the information about spectral classification. Okay.
No problem. I can just put
Then that's okay. It's okay, all the slides are shared with Priya's people. Try to make it bigger than we can. So what happens was the first iteration in this, what is this I will tell you? It started from some error and gradually this is about 10,000 iterations. Just come down to a very low and then it sort of becomes asymptotic. But you see, these are instabilities between the. So certain kind of applications don't even show this. It's a very smooth thing. But in general, you should not stop the learning here, for example. It's unstable. But yes, so this has to be checked. In case of supervised, check that you are at the right position where the errors have come from. Trust. So this is a test we always do. And slide is not changing.
Yeah, it should have.
Shows us. So yes, so I was mentioning you, train versus train. You see? So these dots are the number of patterns. In this case, it's about 160 or so. So all the 160 patterns in the training are perfectly coming when the ANN has classified. And see, they are exactly on the diagram. If here some outliers are there, which means your training has not been good. But this is not an ideal case. Many times this may not happen, even after long training sessions. You may not get everything. But as far as possible, this has to be maintained. Then this is not the test set. In this case, here there are 158 or something. In different, so let's say ABCDs are all 58 different patterns. So this is a big library of almost 850 patterns, all mixture of various. So you see, there are some scatter, but since this is a 2D plot, you don't know how many of them are on each plot. So unless you make a three-dimensional picture, which I will show. But yes, also, and you can do this chi-square and find out what these numbers I will explain. So essentially, these are the outliers. And when we started this kind of research, the referee used to ask, how do you explain these? So there are two possibilities. One, the training has not been good, but in this case, the training is good. You can see that. But the outliers will be for two reasons. One is the classes of the test set were wrong. Whatever is humans have classified. Or they are genuinely some a new set of spectra with a different class. So this is actually another way of bringing out new classes. Now, that is what,
We just wrote it up
so,
because it's PDF.
maybe, sure, anyway, so as I said, this is of course I'm repeating all the waves are this thing. Internal so let's so It was almost 85-90%.
System.
So that was the kind of success rate those days we were getting. I think rather than showing this list, I will actually start showing the results. So these are all kind of things which we. So now look at these two pictures. On the left, you have O type very hot star. You know O, B, A, H, K. So those are the nomenclatures for hot cooler stars. And there are several stars with slight changes. So why I'm showing this, in the next few slides I will show this. But for the moment, suppose you don't, you skip this number O, V and all. But human eye and human brain knows that this is the shape for our star. And as we go further, the cooler star atmosphere has more and more other metallic gases and so on. And you start seeing this, and also it's a black hole. You see, this overall curve is a black hole. So this peak is slowly shifting towards redder brilliance. This is the brilliance. You see, so if this is almost G and K, the suns. Sun is on this kind of star, and K are stars like yellow stars which you see in the night. Maybe we have a star visible. And you see the way it is changing. You see the shape has changed. So when you forget all this, by the way, these are not actual numbers, they are real features. So if I close everything and then try to again flash them, more or less 100% all of you will say at least this order, not for the final features. So that's the thing. And what we did, we decided that now, of course, we are doing Python and other things. Computers play very well with numbers. This is the easiest thing. So this is an example. If there is a star, so their main structure type is coded in this kind of simple form. I'm not going to that. And so this is the way. So for example, this is a star structure type and this is the luminosity class. So B2, 1. So that will be our sun, similar to this time. So these are the two numbers. So the computer knows these numbers. Each spectra will have a specific number. And it is learning on it. And also remember, first two digits, if I classify like this doesn't get an important because it's the fourth digit. So rather we did reduce. I didn't do anything.
Sorry. It's reconnected.
So those four digits, so say 5205 dot something. So the first three are structured. So O is say 100 and like that. Those codes are there. So, but then we did two things on us. One is break, allow the network to first learn the three codes, and allow the network to learn the last. So that we do independent channels. And I frequently merge that shows some results. So yeah, at the bottom you see this loading done. 90%. These are also places where the human classifier, he or she would have done some error in that. So that also actually comes out. It tells that maybe the human classifier was wrong. And see, there in the scatter plot, each dot doesn't tell how much. So we have to do this kind of three-dimensional plot. This is actually MATLAB, and this. You see, there is a small peak here, there is a whole set of outliers. Most of the data are on the diagonal, and of course, it also tells that maximum number of stars were on that particular category. So this is on our own social library in the US, we call it. And you can see it's not so good, but you can see all the points are on the diagonal. And this higher peak means there were many more cool star spectrums. This is another such plot I will just. Okay, then there is something called how reliable is your classification. So we did a whole study, this has also been published. So there are various ways to check, not just human classifier, but this. And this is a result of that, which is the best way of classifying. Again, you see PCA comes here. Yesterday, Kumar gave a slight hint. See what happens in the night when you're observing from 3,000 angstroms to 8,000 or 7,000. You don't have a single observation for all the spectrum. You take it in bunches. Many times there are gaps because gradient position or other, whatever reasons, or maybe the night was not here. So you lost that amount of data. So your data is there. It is there, and then there is a gap, and again. So there are several gaps, which is not good because ultimately you need the full spectrum as I said. So this was something where we used PCA itself as a tool to fill those gaps, or rather, as I would say, restoration of the spectrum. How am I doing all the time? Because I started a bit late.
Yeah.
Because after this, I want to show the exercises also.
50.
Yeah, thanks. So these are all the restoration errors and so on. And you see, you can see this darker line. This is where the gaps were there and they have been filled up or old stars. So this was another interesting application. I mentioned about parameters. The stellar atmosphere has temperature, gravity, metallicity. So this was again an application. You see the scatter is not very slow. And here there is more scatter, but histograms tell the quality. So we could extract this information. Sorry, skip this. Then I mentioned about the interesting astrosat came much later, but originally this satellite never took off, the towers. But that time we knew that it would take off, so we could plan a set of theoretical analysis. So you can see that when you have a band filter or a spectrum, band will has less information, but the spectrum has more data points. So you see the kind of errors we got at the things that are fitting by AN and different. So this was again a good exercise as a preparation for the satellite launch or for the better exercise. So you see the quality of the classification errors. These are the things, and we could also get the color access, which is, if you go deep, it is actually the indication of how much dust is there between you and the star. So you can see the quality of extension accuracies which we could predict. And again, the 3D plot shows the number of stars of each scatter. So you can see that. So this is our version of star galaxy, which we did on a limited data. You see how many are stars and how many are galaxies and what is the result by using band and flux. So flux, of course, gives a better thing because you have no full information. This was somewhat later, about 7 years back. This library, Ogle, forgetting the full form, has thousands of. So, for example, there are almost 1 lakh light curves. Now, there is no spectrum. This is the variability of the star. Tia is an expert on that. So we have this huge library. And now we are trying to classify which kind of fluctuation of the light corresponds with that kind of variable star. So this was a good exercise we did. And this was in the, I think it was in the infrared light curves. So for example, this is about 1, 4, 5, 6, 7. 7 different types of light curves. When I say light curve, the star is reducing its intensity way over the side. And they are obviously different. These, in fact, none of them are same. Really speaking. So again, by now with so much of discussion, my ANN, the neural network will learn these curves as patterns. And then when an unknown light curve comes, even if it has gaps, it can fill it, it will classify them correctly. So this was a good exercise we did in the recent years. So yeah, this is something which I'm not so much in the field, but I was more of neural networks, RNAs, and various things were tested, Astropy and so on. But you see, we used, so in the exercise I am giving, original MATLAB but now in Python. So there is a normal ANN which we also developed, but it's available in the Python. Then there is something called support vector machine, Jain-based, random forest, and tree. All these various possibilities are tried, and all of them give different results. Some are good, some are not at all good for this type of input data. So the next one shows, you see, these are the curves. Again, this technically without period information, with period information. And 3 different colors, raw data, PC, less number of PC, more number of, these are different levels of efficiency, and we can reach almost 90% efficiency. And here there is SVM, name, forest, ANN, tree, and some more are there. So you see, each one has its own way of handling the classification. And in this case, of course, the tree has given the best result. But it's not important, sometimes forest may give a better result, and so on. You will be actually, I will be giving an exercise soon after this talk. And I hope in every audience there are a few bright students. I'm not blaming others. At least I don't have a tutorial session because, so this is an exercise, I will give it to you. It has, I will come to that, where you can use these tools and see how good you can analyze. Again, this is related to that. Again, PCAs are easily distinguishing different bunches of different types of scalar variabilities. Now, this is almost as I mentioned about the Lamos, which has millions of spectra taken by the Chinese telescope. And see, this is, I don't know, 15 lakhs or something. Right now, we have used a limited amount where the spectra has a better signal. So that is another interesting any spectral classification. So actual observations have a lot of noise. In theory, it's a smooth thing. So one way is to add, and we have done that. One way is to add 5%, 10% random noise. So a smooth curve will start becoming noisy. And at what level your ANN, whichever tool, stops analyzing to a good efficiency. And that's very important because all the lights are not same, all the telescopes are not same. So you have a limitation to your own code that at what noise level you are still able to classify. So this is, for example, a particular, again, I like yellow cool stars. This is a K-type star, and you can see the quality of the spectral level observed by earlier observers, and almost see they are quite well matched. The blue and the other one. And this is the kind of, and see, even here we had to do this. So the diagonal talks about the diagonal lines, but there are outliers. The peaks don't, this 10,000 stars in that particular class and so on. Okay, see, this is the kind of table I would like you to do it in the exercise. You see, we tried ANN with PCA, without PCA tree, with PCA forest. And you see, I have highlighted this one gave me 71% efficiency with the errors. So, this kind of variations are possible in different tools. So, okay, now I almost come to the last slide of the main talk. So more releases are there and more. So we have a Chinese collaboration and still going on. And as I said, these are the new things which at least we have not started. Kimberly and his colleagues have started using deep learning, quantum probability, and these are of course there I mentioned. Just to the end, I should say only the last 1 year I started using Grok, but the caution is the result which you get, you should ratify it, or rather you should say that it is correct. So I have been working on, so that's another subject of my interest. My career is an interstellar trust. And we do a modeling of what kind of material. So why I'm saying that, some of you are interested in that Japanese actually blasted an asteroid a few years back and got the sample back. The first one was tough, they got very little sample. Because they never realized the surface of the asteroid. Is it hard or soft? Is it like a desert that the satellite is seeing? So first time they had that problem. But next time they were more careful. And we, another subject, I have another good talk on that. We can model it from just the observations because you are not reaching the asteroid just today. So you have to take a lot of data and predict for the what's it called, flyback mission. That you be prepared, it will be hard. And each asteroid is different because they originally have come from different origins. So the second one was Hayabusa 2, and it was a different asteroid. And I have other talk on this, where you can see the thing was brought to Australian desert and the Japanese are carrying it. So that's one part of the story, but then they do chemical analysis of the rest. So what is happening? Many of these things have. So you have always heard the basic thing about origin of life and other systems. Earth is one thing, whether it was a unique thing. And there is a person, he's still alive, he was in the Nalika stage, Vikram Singh in Cardiff. He had promoted this idea that life might have come with comets or asteroids and they have come to Earth. This is one person. And that was almost dying that, but very recently they have found this organic materials in these things. So that's one part of the story. Another part is there are some objects which are planets are forming. There is what is called debris, which is a small parts of the dust of that, where they are formed organic materials. So very exciting thing, and his theory has been again coming up. So this is very much in the game. And again, for this one, I started using Grok. The idea was to give a result using some of the tools. But the basic idea was what is observation, is polarization, and the intensity. That has to match with your rock or whatever. So these are the new things, and I thought I will give an overview of this almost 3 decades of history of the neural network application, which is today called AI, machine learning, and God knows what. But ultimately it started with that. So what I will do, Priya, just one second. Can we go to the presentation? We can take the questions later. Let me quickly show the things. Okay, next one, exercise. So what I have done here is, I have 2 sets of spectra. One is for training and one is for testing. So the idea is she will share, there is a zip file where all the data sets are there. And then I have given just for the heck of it, I have given a sample Python code. You are not worried if you are Python, that's what you will be able to solve. Because Python does this crazy things. Yes, thank you. It does this crazy thing, version within 6 months it will change and it will have some errors. Those you have to sort out. I have given one example so that you know how to approach it. If I really give it as a project, I would not even give that. You should develop yourself. But think that's you should try it. So this is the thing. This is a project you taken as project. It involves using of supervised learning and using Python. The final output, like I showed, should be an XY scatter plot and also possibly a 3D curve. So I'll just explain the things what I've said. These are the 2 references. One more is there. This is our paper in 94, which I started with Rock. And this is the US library, which we developed in 2004. So these 2 references are there. If you can search on Google, you will get the site, you will get the data. But just for your convenience, I have actually in the zip file the data is already. And this CFLib Z-test set of spectra and the learning is by this. And we have about 850 such spectra which are the test. So you have to use your matter but now by the value. And there are several neural networks available. So you have essentially do the following. There are two set of spectra quite different telescopes. So you have to come to what is called a common point. Otherwise you can't go. Otherwise you will think it is doing black holes. Essentially, the spectra is large, 3600 in the almost near ultraviolet to deep in the red. And it has the one level has every angstrom data, but the training one is much more poor. So ultimately, you can't do the reverse. If there is a poor resolution, you can't make it shallow. But the high resolution one, you can bring it. So that's the idea. And ultimately, everything should be uniform and finite. So from this region to this region, every 5 angstroms, you will have a data point. And see, computer knows this as a pattern. It doesn't know what is a hot star, so it doesn't even know what it is. It only reads the numbers. It's a pattern which it is learning. Even the x-axis, the wavelength is not a problem. Except that it should be perfectly in the same platform. So, as I said, this is a very high resolution, our own library. To be degraded, and how to degrade the spectra? I'm not showing the steps here, you have to use a convolution. And two Gaussians can be controlled, very basic mathematics. To do that, and quantitative has to be brought to much poorer resolution. And then next step is it's all inside the value by Python formula, 5 angstrom steps. And then both should start and end same. This is the resolution file. And finally, you should normalize to 1 at the why this level? Because the human line, the V band, yellow green band as a visible band is peaking at. So that everything comes to one single cut. And then you can start the end. And these are the different things. 1, 2, 3, 4, 5, 6. But there are more. And this is when we put it, but I'm sure in there are libraries in Python which have all these things and some additional ones. You could try all of them, some may not work, but you will see comparative results. And in this case, probably tree or forest, they will give a good result. Good old ALN is also. So, just recapping everything, you have to train on this library. It is a test library. We do all the pre-processing. So the training has 158 classes. Okay, the test has 850, which is a mixture of all this. And so this data file class.dat tells those 158, each of them are single number. So each one is O, B, or whatever. And there are missing classes also. This is another interesting thing that kind of star has never been observed. But the ANN can tell that there is a possibility. And if you find it someday, it's a kind of a learning. And then they are defined in this class.dat. And the other, this has 850. So basically 4 files are there, the actual data, trainfile.dat. And how to do it? On that time you can do it much more smarter maybe. So there are 158 spectra, right? What I did was we put them like this, one after the other. And like a single array. So Python or whatever can read this. But that time we did it for on a different way. So both the train pad and test pad are set up there. And if you see a Unix WC command, you will know that there are 850 and there are 158, and with the number of data points are the set. So that is the basic information. And then, so these are from the original. So this is the website where you can see, read more about this. Training library and the other one are already in the reference. So these are read and pre-processed. Finally, you have to get the scatter plot, and if possible, to reverse, which are very easy in Python. And then make a final table. At the end of the question, you make a final table, which one has given the best and improvements. So, yeah, I think I'll stop here. And so I've done both the main talk and then exercise, which I actually developed last time. So it's not urgent that everybody does like your tutorial sessions, but if you think some of you who are interested and you can do it, and I'm there tomorrow till almost 1 o'clock. So if you have any difficulty or you can show some of the results on your laptop, it will be nice. Thank you. Now we can have some questions.
Yeah.
Yes.
Yeah.
While coding the model, that A into 1000 and B into 100 and C into
Yes.
why that complicated model? Because the A classification was having 7, B classification was having 9. To choose single is like 100, 10 and 1. Then also the unit is want to go in the test.
Hold on. What you are asking is why so much is. So you should remember that when is A9 or A5, it's a different spectrum. So A9 will be, let's say in this case, or in the code, say 3, 9 something. And A5 will be 3, 5. So each of them have to be given a user number. Otherwise it connects.
At the constant 1.5.
So that last 3 digits into the decimal is the luminosity. So there are 5 luminosities, super giant science and so on. If you read the basics, you will
That was constant thing, that want to change now.
it will change. Each spectrum will have a different spectrum type and also luminosity. So these two have to be separated out. Then to be say and combine them and tell how good is your classification in terms of luminosity and so on.
And people were putting the input A, B, C, and then this 1.5 was simply added.
Not added, it's giving classification Roman 1 to 5. 1, Roman 2, Roman 55. It's another parameter. It's all hidden in there. Any other?
And so second one is that if you use A and M, then the efficiency was much greater, error was less. But when you use A and M plus BCA, the error was more and the efficiency was vertical.
So simple answer is with PCA the error is more because now you have the huge spectrum reduced to less number of points. So you are taking the most important information, but some of this you are missing out. The whole idea is if it's a very big network, it will be tough, so with the parameters. So I would still advise PCA was only the first try. But ultimately you have to use the whole thing. This is only computation intensive also. Yeah. Any other question? So this exercise will be given by Priya, and at least you have time till 1 o'clock tomorrow. If at least one of you or two of you jointly do this project. I'm there today till the afternoon if you have time, or at least in the night you can try that. Tomorrow I can help you if there are some difficulties. So yeah, I don't think there is any more questions, so let's stop.
Thank you. Let's thank Professor Ranjan. Thank you. Thank you. So as per the poll which we did today, mostly, I think nobody said they know Astro. So we're doing a short Astropy session after which we can. मुझे please का mic
नहीं हो इसका माइक बंद हुआ है ओपन है
इसका बंद ही है इसको बंद करो
ये माइक मेरा
स्टार वॉच कब है
स्टार वॉशिंग है
कब है बेटे काफी 2 दिन वेट करती है
बस अंधेरा होगा बजे आकर सेट करेगा Hello, yeah. So we'll do some very basic stuff on Astropy, because what Professor Chetana will be doing is it requires you to do a little bit of Astropy. So I suppose that most of you know Python, right? But when we had the Google poll, almost everybody said you need some basics on Astropy and VOPy. Okay, so The whole idea behind this is that astronomy has gone from data poor to data rich science. There's a very famous joke where an astronomer, physicist, and mathematician are standing in Scotland and they see a sheep, and it's a white sheep. And the astronomer says, "Oh, all sheep in Scotland are white." So the physicists say, "No, we can only say that this sheep which we are seeing is white, others could be of any other color." The mathematician says, "No, you can't even say that. Only thing we can say is that this sheep which we are looking at it from this side is white. It may have spots and different color on the other side." So astronomers had a habit earlier of making observations. The observations were less, and on very few observations they made conclusions. And that was essential because that was the nature of science. Then we did not have data. But today we have all these large surveys, ground-based telescopes and space-based, and we have tremendous amount of data. Over the years, it has been growing. Even when, say, 30 years back, we were observing a cluster, you could see only a few hundred stars. But now their telescopes are better, the CCDs are better. So you see that there are thousands of stars in each cluster, not tens and fifties and hundreds, but there are thousands and thousands, right? Like the Pleiades constellation is seven sisters. They are not seven, there are many, many there. So when you have so much data, the only way you can do is use computers, right? And for that, Python is a popular language these days. You can use any language to make sense of the rich data. Like Professor Ranjan Gupta said, they have code written in Fortran and C and so on, which works. But Python is getting very popular and it is much more efficient for various reasons. So we'll start off with this. I'll share this Jupyter notebook with you. Suppose most of you are familiar of using Jupyter notebooks. It is a matter of choice whether you want to use PyCharm or Spider or what. But uh, for this session, we'll have. Okay, just a minute. They can hear me?
Yes.
Yeah. Not the one.
Your net is connected, huh?
Net is connected. Where the hell is my?
Not a Python. These are Python.
No, no.
Never mind.
Desktop.
Your edu files. Jupyter notebooks, but no.
No, no. Yeah, this is the one. Manu it. Yeah.
Astropy cosmology, that is the Astropy
Yeah.
tutorial. That's it.
This is it.
What's the
Okay.
Hmm.
So, what is Astropy? It's a single core package for astronomy in Python. And we look at some very basic things here so that you can understand how the whole thing works. You have Astropy units. So these defines all the units which are used in astronomy. For example, yeah, so units, for example, light years, AU, parsecs, kiloparsecs, and so on. So Astropy units handles all that. Then we look at Astropy coordinates, which looks at the coordinate system, alt, azimuth, RA deck, galactic coordinates, and so on. Then you have Astropy tables. You store most of the data in terms of tables, where you may have a list of, say, globular clusters, their location, RA and DEG, their other properties and so on. So you'll have multi-column, multi-row data, and these are stored in specific table formats. So tables, you can make it in various ways, Excel formats or comma-separated variables, tab-separated variables. There's also something called virtual observable tables, VO tables, right? And these allow, say, take only a section of the uh, table from certain row to another, or a table with only you delete certain columns, or you multiply a certain column with something and add it to something to do some mathematics from it and so on. So these VO tables, and they allow you to handle all that. And then Astropy fits. Yeah.
When I read a data, with the it does a very good job. When some goes bonkers, it thinks everything is free and it does mess with it. Then you keep on doing this and you try to do this.
There's no database that you keep it in CSV, your structure. Then they done that.
Yeah, so if you save it, and nowadays virtual observatories is giving data in a format which is very well readable by this thing, that pi VO and all. Yeah, so as you are transitioning from one system to another, there are things being developed, and many things have become simpler now, and there are maybe issues, backward compatibility and so on. Okay, so I have put in this notebook some resources, learn Astropy documentation. If you click any of these links, it will take you to the location and you can see these tutorials. So there's a lot of community which helps you.
Nothing, just continue.
Yeah, so like you all know that this matplotlib is something which we often use for plotting and all. In this particular notebook, we are not plotting anything, but just as a habit, you can import matplotlib.pyplot as PLT and import numpy as NP. Numpy, I'm sure you are familiar with. How many need help in numpy or numpy? Others know. Okay, be good. So that's why we'll skip all that. So NumPy, pandas, we are assuming all that as you all know. And if you don't know, we'll give you some PDF files, and on the basis of what we are showing you, you should be able to learn it yourself. Or you can always approach us later online, or so we'll help you out with that. Okay. But most of the people here know. So you can so you execute it by shift and enter, and you can see what kind of version you have. These two commands tells you NumPy version and AstroPy version, and you can, if you have a very old AstroPy, then you can update using pip install AstroPy upgrade. So I will not do this because I did it in the morning. And now coming to Astropy units. So from Astropy, import units as U. This is something standard which we all know. Import something so that you don't keep writing units all the time. You can just say U dot whatever. Yeah. So So for example, now I'm having distance 1, I'm defining a variable and I call it 1 into u dot au. Yeah, so capital A, capital U. But the units is U because we've imported units as U. And so I'm this variable which oops, why did it? Yeah, I probably didn't I run this one? Yeah. So now so as you all know, here we put in units as distance 1, and when I'm reading it out, print or you can write as a 1 and showing the value. So from example, this one will be in 1 unit. If you want 10 AO, 10 AO. Okay. So similarly, for light years, as you would have guessed, it should be U light year. Yeah, light year. That does it all. Okay. Similarly, you can put parsec, PC and parsec, U dot parsec. Right? And you see how easy it is to convert. So one this other variable distance to which you have here is in light years. And if you want to convert to meters, you say distance dot 2 meters, right? Distance dot 2 centimeters. So it convert this is converting light year to meter. This is converting 1 light year to centimeters, right? So it's as simple as that. You don't have to do much. And similarly, okay, so run this, run this, run this, and now I'm defining this unit u dot parsec. So suppose, yeah, this didn't make sense. We could have said some x is equal to this. So now x would be in parsecs. Okay, so distance is in parsecs, and you convert that dist to meters, and there it is. Yeah, so it makes your life extremely simple. And similarly, you can convert it to light years and to parsecs, and so we are going from parsec to parsec. You so come back to that, isn't it? So right, dist, whatever the variable is, dist dot to and specify. You just see a slight difference. If I'm using the word meters, suppose that unit is for meters, when you got meter, then you don't have to say any problem. Okay. So similarly, when we were having this light here, when we have that unit, convert to light like this, but rather I can just do it with a u dot light here, right? And similarly, we do it for all this. Okay. Yeah, and then you can also have an array. For example, I'm having various distances. Distance 1, 3, and 6. And then I can convert all of them to linear or offsets. So I can just multiply in numpy array or list directly by, see, distances. I have 1 comma 3 comma 7, and now I'm converting them to distances in light years. By running this, I'm defining another distances underscore variable. This is a variable name. You can write whatever is suitable. And here you are seeing, now you have the whole set of things. So if you have to do some computations for many different light years or parsecs, and so you can habitize these things. And then you can use the NumPy things, which is the maximum distance of these three, and what is the mean of that. And so now you are falling back on the NumPy and all the functionality of that, and you can do all these things. Okay. Another recommendation is it's better to define the input quantities with units, right? And it helps us to do computations, and then finally do the conversion at the final one, whatever you want to do. Yeah, this is just a suggestion. And for since these standardized units, you have these SI units and CGS units. So distance one dot SI, it's converting to the SI units, and this is converting distance one to the CGS, right? So it is as simple as that. And similarly, when you are converting from Celsius to Kelvin and Kelvin to Celsius, you can use again similar functionality. Temperature is 25 U Celsius. And just be careful wherever you have capitalization. Python, as you know, is case sensitive. If you write a small c there, then you may have a problem. And right? So when it is capital C, it is capital C. Yeah. Similarly, Kelvin, and you are converting to degrees and so on. Astropy also has a lot of constants stored there. The list is tremendously large. You can use the constants in that. So from Astropy, import constants as const or whatever you don't call it as C, because C is used for speed. So you can give import constants as const or const or whatever. So, okay.
Does it?
Yes, Armstrong. It does all those, yeah. So the list, I think I have somewhere where you can see all the list. And not just like, for example, const.c is the speed of light. Const.r underscore sun is the radius of the sun. Similarly, here, as you can expect, if I have, say, mass underscore sun, it will give you mass of sun. Okay. Similarly, you have mass Earth, mass Jupiter, mass various things. So you don't have to go to the net and look for the masses or remember them. All these things are right there. So there is a link here which gives you the available. It will take you and you see you have G, the capital G, gravitational constant, and Avogadro number, and gas constant R, and etc. etc. So the list is pretty big. All that you require should be there. GM of Earth, normal Earth mass parameter, GM for Jupiter, GM for Sun, and radiuses and various. The list is pretty big, and you can look at this. So yeah, so again, I'll just. Okay, now coming to this coordinates, astropy coordinates. Yeah, this is also very helpful. This is for the coordinate systems which we use in astronomy, from alt azimuth to right descension declination to galactic coordinates. All these gets converted very smoothly. It's all there. So from Astropy coordinates, import sky coordinates. Okay, so remember, sky is capital S and coord C is capital C. And the good thing about Python is once you make a Jupyter file or a certain code in Python, you can keep reusing that for different objects, different things all the time, right? So the kind of things you often do a person studying galaxies will be doing similar kind of things, person from cosmology. So they have this set templates where you keep changing the objects or making loops and doing repetitive calculations. So, and then it becomes your second nature to remember that sky is capital S, coordinate quad, and so from Astropy, I am importing this as sky chord. You can even call it SC or SKC, whatever, but I'm calling it sky chord. Yeah, so no, sorry. You can import it as further, import this. I can further put as something. And then you needn't write sky coordinates all the time. And then you can start using SK. But let me not do that because it will mess up my. Okay. So, for example, now I'm defining a variable called position underscore crab. So, position of crab, and I'm using the sky coordinates and 83.63. I'm keeping it in degrees, RA and declination, both in degrees, as far as using unit degrees, and frame is RC reference system. And now, how do I do this? You can Google search and get this thing. And so I from the Google, we get this, and we are when I'm saying print position crab, it is giving me the same thing. This position. This is in degrees. So you can. So you can even convert it from degrees to galactic frame. KD is into the galactic frame. And detail into the galactic. The sun, if you from sun, if you look towards the galactic center, that is a zero longitude. And as you go 90 degrees, it goes around 360 degrees. And the latitude is from the plane of our galactic plane, 5 degrees, 10 degrees, and so on, 90 degrees. And the minus are downwards, right? So from sun to galactic center is zero longitude. Anti-center, your galactic center is Sagittarius A, 180 degrees away is 180, right? You understood. So if this is where Sagittarius A is, and this is where our solar system is, this is zero longitude, and then you have 90, 180, 270, and back to 360. Okay, so these are the galactic longitudes, and latitude is how high you go up the plane, positive for the upper side and negative for the lower ones. So you can, so this is, you are getting crab in terms of from, yeah, so it's very simple to go from one system to another and so on. So alternatively, you can also have them in terms of hours, minutes, and seconds. So RA and declination are given either in degrees, or you can convert them into 5 hours, 34 minutes. And so in the previous one, we had coordinates in degrees, but here we are doing it in unit hour degree. Yeah, so only while your declination is in degrees, you can have that in hours. Okay. So here you have these things. In fact, in the previous one, we got the coordinates of that object, the Crab Nebula, from looking at the internet and getting it and putting it there. But there is another way of that is name. And here you would put M1, then feature. Or you put the entity number. Entity. So from name, it can get the coordinates, and you see that it is the same thing, right? So we can this function this
Hello.
you see we get three in the net this game. Similarly, we can do it for any other object, and here is an example. So M13, the globular cluster, I am using the position, giving the variable position. Okay, then M13. Okay, and it will give us its RA deck for that.
Hello,
And
Professor.
like we had done this earlier, you can convert it from RA deck to galactic
Hello.
just by using transform to galactic, and it is giving you the equation M13 in terms of the galactic longitude that, right? So otherwise it's a lot of messy calculations. All the thing is done directly. It's very conveniently. Okay.
Hello, Professor Hasan.
Realize that there is another way of doing it when you position underscore M13 dot galactic. Okay, so my time is running out. And similarly, you can convert it to RA index by just dot ICRS, and it does it. Okay. And yeah, so I'll go ahead, and then you can see it's only longitude and latitude. So dot, once we have position of crab, data dot long, data dot lat, longitude, latitude, and it's just giving you the longitude and latitude. Okay, extremely comfortable. And here is a small thing where you can find the separation between crab and the Sagittarius A. Yeah, so I'm defining position of Sagittarius A and doing it here. Okay, you have a look at this. You can, this is again interesting. From astropy.coordinates import Earth location and alt azimuth. And from astropy.time import time. Okay, so this will give me, so now that I'm in Hyderabad, one way is I say Hyderabad Earth location, I specify what the latitude is in degrees, what is the longitude in degrees, and I print Hyderabad's geodesic. And then when I use this time now, it will give me the time in Hyderabad. It's giving the date 24/3/2026 and 5/18/25. You may be thinking that it is doing something wrong. It is 10:48, but this is giving it in the Greenwich Mean Time, right? So at 5.5 hours, you'll get the right one. And once you know the location, then it helps you convert from RA deck to alt azimuth and so on and so forth. And also, now that when I want to find out, I have this position crab is the position variable for crab which I've defined, and I say transform to alt azimuth. So presently it is telling me where is the crab nebula. It is 64.62 right ascension, and declination is -6, so it's below the horizon. Yeah, azimuth, alt and azimuth. So altitude, yeah, it's above 64 point. It's above and uh, minus. Okay. Similarly, you have small this thing where we are importing tables, and the first table I have is a blank table. That's why it's printing nothing. But I can construct a table this way, since you all know Python, this is something very similar to that. So I'm putting 3 Scrap, Sagittarius A, Cassiopeia A, Vela Junior, Andromeda, and I have put their galactic longitude, latitudes, and one is a it's a supernova, a remnant galaxy, or an unknown object, or and so on. And this is your table, and then you can access a certain row, you're accessing only the columns of it, you're accessing only the longitude of certain object. So you can do all these things very well. You can see only 0 to 3 rows of it. You can cut down the fourth one, right? So it starts with 0, 1, 2, 3, right? So there were 4. I've dropped the fourth one, and then you can do various. Okay, and then you can write this into a table, and you can write it in FITS format. You can write it in ASCII, ECVS, enhanced comma separated variable format, and you give the file name. So it will write it, save it on your disk. And if you want to read, then you use the table.read command to read these things. Okay. So then you can group by, and you can sort out this table according to ascending, descending order, and you can remove a certain row, and so on and so forth. So finally, coming to the FITS format, FITS is flexible image transport systems, where you bundle up your images and spectra and various things. And we are looking at fits.open, gets you to read this file, and you can get the HDO list information by using this command, and then you can store the image. The 0th one usually is the image, or when you use the header file, you understand which one it is. And you can use matplotlib to plot this. So this is at Cassiopeia A, and you can see the header file information, various things, and you can convert into world coordinate systems. And okay, so this is a brief and short introductions. The big boss doesn't let me continue, so I'll have to stop. Yeah. So I'll share the files and the Jupyter file, and you can run it and see. It's not difficult at all. Thank you.
I think there's anything. I'd like now to ask presentation. This is Professor Hasan. I was supposed to mean because basically, yeah, Chetana started very tight schedule. She has to finish talks before lunch, and then she has lunch, and then catch up like in the back. She can't really leave the mornings. So that's why the problem. So that's the thing. So Chetana start with the theory will be right? And then after T, since you are going to be lunch, then change the answer. So over to you, Chetana.
Yes. So,
Share.
Okay, तो यार
कहाँ गया वो?
back to meeting, and go back to meeting.
Share.
Where's that thing?
This one?
This one, yeah.
hello.
So now I think you'll get time on that you citation and diagram. I mean, you can space it at one, but then now till 1 o'clock, it's yours. So good morning, everyone. So the first session will be on the basic theory that I will be requiring for the session. So this is astrophysical environments. Where's the? It's on. Yeah. It should work. Okay, one second. You start up there. So what do we mean by extreme? So whatever is here is based on neutron stars, black holes, compact objects, and this X-ray universe. By extreme, we imply extremes of temperature, extremes of magnetic field, extremes of energies, and gravity. Yeah, you can continue to. He'll give you. So, for comparison, I have given. Right. So, for comparison, I have given temperature values here. So, room temperature, everybody knows how much is it in Celsius. So, we have written it. 5,000 feet. So, it's 6,000 feet. But we are talking about extreme. So, so we are talking about extremes of temperatures, about millions of kelvins, 10 to the power 7 Kelvin. Now, so energies, lab energies, few electron volts, we are kilo electrons, typically 10 volts. Magnetic field, power magnetic field, 100 volts. We are 10 to the power 8, 10 to the power 12 Gauss objects, 10 to the power 15. So these are the extreme limits that there is. And in this sense, there is limitation of time, days of everything, which is not possible. But I will concentrate on whatever is required for this workshop. I will give you the basic terminology. What are the objects that we are going to talk about, and why are we doing whatever we are doing? And why is it important? All of you must have seen this image somewhere in your Google search. Whenever we see an object, we need to study it in different wave bands. UV में देखिए, optical में देखिए, X-rays में देखिए, in different bands, and make a complete story by giving your inputs on how you describe that.
Hello, ma'am. Zoom is not running.
कमिटी असतो मीटिंग वेळ समजा 24 तारीख पर घुंची होने ना वो घुंची पड़ी घुंटा कौन पे कोई पे कौन पे रुचा कौन
and when is the object near the companion, when it is away from the companion, lot of terms. Another thing, so once you have determined the orbital period, again, we did it for spin period. We had spin period and now it was involved. Now we have orbital period and how that orbital period evolves. Determine the period today, 2 years or more. Subtract will tell us a lot of things. For example, what do you think? Should the period of this any binary be constant, or should it be increasing or decreasing?
Increase the mass rate should be increasing.
Why should it increase?
The spin rate should be
Period.
then the orbital period should decrease.
How is the orbital period related to spin period?
As soon as the mass of the period gets closer,
There is more energy in the system, so the orbit expands. So orbital period will increase. Anything else? Any other? When will it decrease? So it was increasing when the energy was increasing. Okay, when will it decrease?
when the mass is lower, like lunar has
Accreted mass is less. When will it be less? Not all the mass is going towards the neutron star. Some of the mass is being lost from the system. So in that case, we expect the orbital period to decrease. So here also, this is called as mass transfer. Mass transfer can be conservative, it can be non-conservative. Conservative implies that whatever mass is being thrown out by the companion, the compact objects is taking all that mass. And non-conservative, some mass is being lost as stellar wind and several factors. So just by looking at orbital period and its evolution, we can determine whether it is a conservative scenario or a non-conservative scenario. If it is non-conservative, then you need to, by looking at other factors, you need to determine what is the cause for that mass loss or what is the cause for that, all details, or we can discuss in the tea break. But this physics comes out only from these two parameters. Quasi periodic. By quasi periodic, and this is accretion disk, you already know now. So there is an accretion disk and there is this white patch. This white patch, size of this white patch is not uniform in the entire circle, in the entire cycle. And this patch is coming arbitrary. So because of this patch, there is some periodicity induced, but that periodicity is quasi. It is not a perfectly periodic. It appears sometimes, it is not there sometimes, and so on. So if in your data you have these things, then you can tell about what is the structure of the accretion disk. Is it a uniform disk? Okay, so we have been talking about data. What is data here? So anyways, we send our detectors on board some satellite, it goes up, it collects data. That data is in some format, like you know CSV, you know PDF. In Astro, we use a FITS format. It is a flexible transfer format. From that site, you do a click, download data, nothing very expensive, and then reduce that data. Threads and manuals are already up there. You need to follow that step, just copy paste. You can reduce that data and analyze. What you want to analyze in that data, meaning in timing, you are determining any periodic nature, any periodic term, or a transient factor. I will come to that. So by data, suppose you are doing time series analysis. In time series, data implies counts, X-ray photons. X-ray photons meaning few kiloelectron volt photons. They are received by your detector. Some count, so count rate. And when you do the plotting of your data, x-axis has time, y-axis can be counts, or you can normalize it and you make it as rate, count per second. And the trend in this time series analysis can be random. It can be no trend. It is possible that there is some baseline and sudden increase. Then there is some dips. Then there is this rectangular shape, and then again constant. There can be several things. Here, in this kind of a structure, you see these spikes which appear regularly. If you see this kind of a time series, you are very lucky. Determine what is the time gap between these peaks. Again, there were these, then some baseline, then again dips and so on. So time series can have different structures. You need to determine your useful information from such graphs. Then in X-ray astronomy, there are two things. We have persistent systems and we have transient systems. By persistent meaning that object is always available in the sky and it never sleeps. Whenever you point your detector towards that, you will see some counting. This is never sleep. Okay, and these are always bright. On the opposite, there are transient systems which are mostly 0, 0, 0, 0, 0, but suddenly it accretes matter sufficient enough to start emitting X-ray photons. So this kind of a system, a transient system, this is a persistent system. Here, if this phase lasts for long, one generally tends to call this as persistent because in that phase there is no other feature. But in transients, generally 0, 0, 0, 0, 0, 0, 0, but in between there is a thermonuclear flash sudden increase, and then that count rate tends to fall and becomes constant. Why is that so? This big object, the companion, it is giving mass. Matter is flowing towards the compact object. When this matter is sufficient enough, but whenever there is no accretion, a dim phase that gives you this zero flux phase. So by looking at your data, if you see this kind of a trend, that means it is a transient source, and then you try to do some physics here. You take out this chunk, about 400 to 1000 seconds of data, and see what is the physics in this region. So this is another way to show you what are persistent and transient systems. So persistent, they are always active. You always see some count rate, although there are in between variations in that count rate, but it is always some count rate. Then there are transient source, which are inactive most of the time, but suddenly their luminosity increases, stays there for some time, and then some time meaning very small time compared to what is the baseline time, and then fades away, and so on. So in timing analysis, we will be doing the variability present in the time series. You will be looking at if there is any periodicity, or is it completely aperiodic, or there is some in-between quasi-periodicity. And looking at these systems, we will try to understand what is the physical mechanism which is governing those kind of periodicities. So in the hands-on, your first step will be to generate this light curve. I will give you a data. You already have that data, file 1 and file 2 with you. So you open that data, plot the time series, and see whether there is any feature. If you see that feature right away, you are very lucky. But if there is no feature, then surgery, which is based on the bin size, we will come to that in the next slide, and then try to see whether there is any meaningful physics in that light curve or not. The first step is just plot that time series. So what is the difference between this graph and this graph? Are they two different sources? Same source. कैसे होगा? यहाँ पे तो count rate is 700, here it is 350, and see the time is 6800 seconds and so on. There, here time is 0 seconds and so on. How can it be same? Normalized by what factor?
Actually, in the histogram bins
So here comes the usefulness of bins. This was the original. You had the file, you plotted it as it is. You saw this, but then this is very messed up. We do not. This is all dark black. We do not know what is the trend here. So we try to increase the bin size. So instead of this, if you the bin size was 1, meaning after every 1 second you are collecting data. But if you are collecting data after every 2 seconds, you get a better graph. Here also no period, this is 0 onwards, so it cannot be the same file.
Actually, this is the satellite tab.
It can be satellite type, or when I made this graph, I gave an instruction to start from 0 of the observation. So do not worry about this time scale and this time scale. So here now you know what is binning. I want these 4 answers from you for this red graph and for this blue graph. This is a sample. This has nothing to do with the astro data. I just made these graphs. So what is the periodicity in the first one and in the second one? Not yet. Everybody has answered.
1 second.
1 second for red or blue? For both of them, 1 second. Okay. Bin time. Point 0.2 second. For red one it is 0.1. Everybody has understood why it is 0.1? It is okay to say that you have not understood, otherwise you will lose interest. Not understood? So here you understand a sinusoidal curve. This is a complete cycle. So see where that cycle starts and ends. ये वाला देखते हैं पहले. Blue is more smoother. So it starts here, goes up, goes down, and comes back in the same phase. Okay, so this is one cycle, or time is 0 to 1 unit. Meaning I have collected data after those many seconds. How many blue dots are here? How many segments are there? 21. Segments will be 20. And here 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 divided by 10, that will give the bin time for red one. So what is the average baseline? It is 5 for red. I am absolutely wrong.
We have to sum up. Like
Not give me the answer. What is the count rate here? 5. 5 चाहिए ना, average है top and this average.
that is like 5 is the variation within 1 second, and we want the whole of the number.
And you know the time of occurrence of the next. Eclipse. It is related other than you need to determine what is the eclipse duration, or you need to determine this eclipse. That constant, this constant part to determine what is the middle point of this constant part, and then time connect this middle point with the middle point of the next. Clear here, because this is very important in your hands-on session. They will give you periodicity right away. And in Fourier analysis, we plot the power as a function of frequency. Do its inverse of that see what is the time. And when you don't make that power spectrum power, and there is something called which is the V2 Poisson status. Second exercise, you will generate the Fourier spectrum. If there is some noise and a signal is hidden in that noise, Fourier will give you a sharp peak. Okay, and if there, but it is not as sharp as this. Okay, and one suppose here wind time. What will be the optimum wind time that you will set in your data? In the previous one, we said, okay, this looks messy. We increase the wind time. Then I said there is no periodicity here. Increase it further and further and so on. What will be the optimum number? It depends on what kind of periodicity of 1 millisecond. Suppose you know that period is 1 minute. Then that millisecond de-binning, you should do a proper and keep your bin size smaller and then X-ray down. And with this, okay, light is also gone. So we'll break for tea. But should install Astropy in your systems and sorry, the T has come. So we are breaking. It's fine with this one. So do a pip install and leave it on your system so that when we are back, these systems can.
We'll set this, but let me.
Yesterday, Chetana was there.
On Friday, Saturday he came. Also he came on Sunday. So today afternoon there is no change. So as per schedule, the guy who's written Top Cat, no Mark Taylor. We've done a lot of things.
Join online.
Yeah, he'll join. He's from University.
Thank you. Yeah, yeah.
Your system. Files are on her system. So I can do it from there.
Okay.
इसमें zoom है.
But why can't we get it here?
I don't have it on my pen drive. I WhatsApp.
WhatsApp her, no? Where's her WhatsApp?
This is yours.
Yeah, I'll WhatsApp from her to me. Yeah, just two.
These two.
Yeah, yeah, that's done. Yeah, put it on desktop. Now you want to go on Google Colab, but you'll have to log in. Hmm? Show me. Add another account. Yeah, now you log in.
Where's that collar mic ले लो.
हो जाएगा वहां जाना ही है.
देखो, connected on.
ये on ही चाहिए.
You on करेंगे.
यार,
Yeah, now it.
आपके पास कुछ आएगा 60.
मेरे पास आएगा.
GT 60 किसका है?
आपके पास है.
तो ये हमारे एडमिनिस्ट्रेटर के पास जाएगा और वो तो अभी मिलेगा नहीं. मेरा ही है.
60.
आपका लॉकडाउन ये अभी आपका ही लॉकडाउन. So everybody is on Google Colab? Yes, no.
Yeah.
तो मैं आपसे वहां पर क्यों गई हूँ?
yes, ma'am.
लॉग आउट.
You took my Google access.
तो सिर्फ
Same con.
You need me to resend the data file, so you've got it.
Yeah, you were there, no? Yeah.
लेकिन then it is accessing your thing. So I will sign in again. Yours is off.
Should I forward it to your email?
No, it is there. It is there.
This is
आपका नहीं चाहिए. This is again yours.
oh, the live streaming is on. Audio कहाँ से आ रहा है निजाम? Where's the audio going to come from? From this, because this is muted.
इसमें से sign out. Sign out नहीं होगा.
This is Hasan. Sign into her.
फिर वो यहाँ पे आप ही का आ जाता.
This is yours only. Exit. Should I forward it to you? The data files, yeah.
Data files are here. We are opening collab here.
अच्छा.
Collab में इनका खुलता है.
एक मिनट.
खोलो.
फिर से भी there's a net log. You can sit also.
Yeah.
And try the it's not start. Yes, no. LC 5.1 LC. So we will begin with 1.LC. If you are very interested, then able to 5.LC. Are you good students? Oh, I use that. सिर्फ कोलैब लिखेंगे तो क्या करेंगे? सिर्फ कोलैब टाइप करेंगे. But what is running in collab? Nothing. If the item not is not there. No. Otherwise, they will only keep the notebooks with them. Correct. They won't do anything. आज तो टाइप करके ही चले. यहाँ से फिर आप.
Add an account.
Chetana. See. Chetana.
ये मैं Firefox में ट्राई कर रहा हूँ.
Zoom करना होगा.
Good.
So is the font size visible to everyone?
You can take.
Is the font size visible? Sir. तो नहीं है.
Sit and go.
No, I will. So now first import the libraries. Write this first cell. Import maybe plotting. So SCID. Dot LC. What was they solve. So here the way is from Astropy in properties. So now side for or you want but it means is this better? Who was asking? Better? Just run the first one. Everybody. Should I come and check? Where it's by something else. Done? Done? Go back. Done. Now, based on where file is, I'm moving ahead, removing this first cell. Where is your file? If it is in your drive, then execute the upper cell. If it is in your computer or laptop, then upload it from there. So either dispatch or dispatch. I've written R again. This is the main file.
So body, this is you are see if it is there, if it is not there. Best is short. See. Then if it is in your system, then it is there. And in the big signal or and the body, right? That also you get was the board. First course is this is very important. I do that. You often misconnect.
On that bana je sabke ग्रहण कर दे
Nice.
घरे चाहला बना साधरे ग्रहण कर दिया
Nice. Yeah. Actually,
ଆଉ କଣ କରୁଛ ମୁଁ ପ୍ରଥମ ତମ
Sorry. I think we are good. Our answer.
Send request, Priya sharing. And you make me a co.
Yeah. You always work for.
Where are you? Which is your file?
Which is your file? Windows, sorry, this thing, na Najam, ye hai. Where? This must be the one, no? Looks like a, no. Ye kya hai? We'll never forget your kindness.
Yeah.
Firefox, you are using Firefox nowadays, I don't know why.
Because
Okay,
that was the
use-
only way I could log in.
Explorer. Where's the color?
Firefox में गए थे. Welcome to Go. नहीं मेरा. हाँ क्यों गया वो वहां से?
Just check whether it's Firefox or is it which one? Here's your Chrome. Are you using Chrome only? Log into Yahoo.
Here it will open live.
Acha. Then to open it here.
यहाँ कोलैब करेंगे.
Google app, Google कर लो. Chat understands. ये कौन है?
देखो साइन इन कर लो.
Who's the guy? Hey, who does it think you are? Yeah, let her.
अभी था ना. How did it go?
I don't know. Can't you log out from here?
It's by default doing.
Okay.
Monday tutorial is there.
ये है. This is the one.
So files are uploaded. We are going to the next step.
This is not shared. Just see the word.
This one.
Yeah.
नहीं, दूसरा
Return to
वाला.
meeting. Hey, this is Zoom. Na? This is Zoom.
इसमें से share होगा ना.
So you return to meeting. It doesn't. Acha, this stop share. It's on a share already. So we will insert share. And let me share the whole screen. Right? Let me look at the screen. Yeah. Done. Sorry.
So next step. You have file 1.lc. Everybody back. Type instead of. So you have file 1.lc with you. And now we will first step was to plot the light curve. So you already have this data file. The first column of the data file, we are calling time. So time is equal to from that data. Data is this file. For that data, take the first field, which in Python we write as 0. The second column is rate. So from that data, take the second field. And these are to plot the light. So type it as it is, and you will see some. You don't need to type again data is equal to fits dot get data. You've already executed it at the based on whether the right or now if you are doing Somebody. Yeah. Somebody. Is it now? Polarity. And if there is any condition was the let us know. Font size is optional. We can only labeling is optional for the tree. Even PID this is also optional. Just not everything what we get. What should be this? What is there anything here? Now, very good. Now you can play with this actually. When you got the light up, like he is not following you. So what did you everybody is not please? You should get this kind of a light curve. Everybody is getting this thing. Now what should we do? What is our aim? Why do you increase the big size? But do you see anything here? There is a peak, but it can't see. There is a peak. Peak to anything else is here? There is a gap here. Which gap? This gap, this gap, this gap, this gap. So this gap detected system and then it got shut down, then it again started. So this gap, you know, we are the same. For this, what this one last one. And this one. Second, part, there was first, there is this, there was then it became zero. Maybe it is one here, so similarly, so what should we say? Increase the size, make it smoother curve, Determine eclipse time. Determine eclipse time for both the eclipse. Determine the difference and what is the period of the system. Okay. So next is this. This is visible at the back also. So here is equal to, here I have not written the number. You need to write. And accordingly, suppose you one after every 1 second we need to data. Now if we need to see for example, after every 5 seconds we can data. So it's a steps. So this step, the step size, then the average 5 seconds data. And now the just to show up when see and new thing we have to listen. Even if you do not have to listen, let us see. In last one, it is already can just plot the item. If something is not is image. So I'm telling you from parts in the person. Others will have everyone. Or today's number in new change that number. See how it is. What's that? Let me know, but otherwise it's in the WhatsApp group. Payments redundancy is time. So very different numbers. It is not. It is not. For that, it is not damage. You are not looking at this great balance. So we can make a depend on your relation and this country. Done? चले आप what you will time take what is the option? 2, 3, 4, 5, 10, 20. What did you take? 100? She took 300 and see what is the problem with that. The profile structure is gone. She got a peak instead of a smooth. So if I take 5, I was getting this one. With 10, it was not better. Is that code clear? What is this code doing? If you put numerator is equal to 5 symbols, then it will determine the steps. Increase the time spent. Once the time spent, then it says earlier it's 1, 2, 3, 4, 5, 6. Now that will be earlier 2, 3, 4, 5, 6. Now step size. So time big, if you bring it, see that it is 0, 5, 10, 15, 20. You can check yourself, break and read and see what is the matter. Is it same as data within those 5 seconds? We are taking average, rate, mean, and delete the rate. And then we are talking. If this is done, we will next step. There is Data. Because now you're making video file. So I will make this graph. You will done. Those who are not answering, done. So this is with 5. Right, 10 is also okay. Because our aim is, remember, determine what is the eclipse time, what is the eclipse time for the second one, difference and period. Just that. So now comes the, I will show you the result first. So in this cell, what I did, there are 2 eclipses. Okay. Look at one, tell me where eclipses are occurring. That's the period time nature of the eclipse. Look at the graph. Now, 2025. Same. So I have expanded the light curve here first and say the English 17,400. Then this is combined. There are products are also with components and so then a constant, then a three, and then a constant. So here a constant, here there a constant, here experiment, going to be what three, here by so you will get this kind of a curve with this cell. So first understand what is this visible or is it correct? So first see how the model is defined. There T is the image. C T4. What is T? C is the also the eclipse content. D is how much is the depth. How much is the degrees from that out of eclipse to eclipse. T1 is when this slope starts. T2 is when this slope starts. T2 is this when the eclipse starts. T3 when eclipse ends. T4 when it comes out of the eclipse. So we need to define, give an initial value for these numbers. And the program says initially y is all constants, whatever is out of eclipse it is there. How much is out of eclipse? How much will be out of eclipse? Suppose this is the expanded view. What will be the initial guess for C? Initial guess for C. What is C? C is which constant? C is this. Before entering the eclipse, what was the count rate? And whenever you do fitting, you provide some initial number value. So what value will you give to C? देखो dots का spread क्या है? Blue dots is somewhere between 10 and 12.5. So you can give 11, you can give 12, you can give 12.5. So C is started or multi-factor. So in the program, in the model, we are saying initially y equal 12 on all the angles. Then if the lines is slowly more then straight a straight line. See? So this is the constant and this is the slope. Area is body is C minus D or then line come up again. So n minus D and again so you define what it was Then tell your program that you need to do the eclipse fitting within certain region. So here is given in 50 and 2450. Look at the next one. And really start take this question. Let's look at the other thing. Give the initial level of speed of what is the if the output is 1, then it will be 11. So 12 round number and these 4 times. So the English stuff is then this is an you already solve with it is already what model and take this. With this simple an eclipse profile and it will give you certain mid eclipse time also. So in this case, mid eclipse time was 2055.595470 seconds. How will you determine this? You will determine this time. This is divided by 2, we use the in between the mid eclipse time. Is this clear? Should I repeat? Clear? So start typing the code. First define this model, then I will explore. There are other models also. This is the easiest one for the workshop. But if you do your research, you can use this model or some hyperpooling or double exponential. There are several models depending on the system is there. Sometimes the eclipse profile is not as sharp as in this source. So then this step and ramp will not work. If anybody is having any problem, then you know. Once you get this much, then I will scroll it up. This much. Determine the eclipse time. Graph is there. I don't see graph of eclipse. Okay. PIT, you can PIT yourself, not to put the data. Please, teaching experience helps. Ah. Share the big of them. So for the data scattered. So PLC, ED and something that scattered bullets. I want to plot them also. So PLD dot x-axis is time, y-axis is number of parameters, and left turn. Then I want this is optional. The more vertical lines is optional. I want to see where even if equal lies. You can follow these two. A scatter plot of the data and best fit of your plan. Expert should come on a speed limit.
So it's not.
So some of you have lost the code somewhere. Check your code. Or this is okay, model, no error. Is your problem resolved? It's resolved. What was the error? Where was the error? Okay, so if this is done, then what is the next step? What is the next step? For periodicity, what do you need? No, no, no. You have another eclipse. Difference of that and this one will give you orbital period. So do the fitting for the next one. So for the next one, M is equal to, look on the board. For the next one, M is equal to time bin greater than equal to, you need to write it yourself. And time bin less than equal to, you need to write it yourself. Guess values, here you need to give it yourself and determine what is the eclipse time. This will be the graph for the second one. So if you have understood the first one, repeat everything for the second eclipse. Copy that. Determine the eclipse numbers. Tell me what is the eclipse time. This is near 16,000. The second eclipse. Beautiful. Yes. Want me to scroll up? Okay. I knew ऐसा बच्चा है. This is the code. You need to do it here on second exercise. So it's P1, P2, P3, P4, everything. Also, it's I don't anything else. It's something I don't know. What the things are something like so that is same thing. Same. I just negate it. Break for lunch. So you have the orbital period with you now. So this is one of the ways that we can break for lunch. Your period should match with 13763 and graph is this. Right? Sure. So we break for lunch now.